Graphical exchange economies. In the same way that the graph of a graphical game represents restrictions on which pairs of players directly influence each other's payoffs, it is natural to examine similar restrictions in classical exchange economies and other market models. In such models, there is typically some number k of goods available for trade and n players or consumers in the economy. Each consumer has a utility function mapping bundles or amounts of the k goods to a subjective utility, setting in which the utility functions obey certain constraints, such as concavity or linearity, are often assumed. Each consumer also has an endowment, a particular bundle of goods that they are free to trade. It is assumed that if prices p arrow in R plus to the k are posted for the k goods, each consumer will attempt to sell their initial endowment at the posted prices, and then attempt to buy from other consumers that bundle of goods which maximizes their utility, subject to the amount of cash received in the sale of their endowment. A celebrated result of Arrow and Debro 1954 established very general conditions under which an equilibrium price vector exists, prices at which all consumers are able to sell all of their initial endowments, no excess supply, and simultaneously able to purchase their utility maximizing bundles, no excess demand. The result depends crucially on the fact that the model permits exchange of goods between any pair of consumers in the economy. A natural graph or network-based variant of such models again introduces an undirected graph G over the n consumers with the interpretation that trade is permitted between consumers I and j if and only if the edge ij is present in G. The classical equilibrium existence result can be recovered, but only if we now allow for the possibility of local prices, that is, prices for each good consumer pair. In other words, at equilibrium in such a graphical economy, the price per unit of wheat may differ when purchased from different consumers due to the effects of network topology. In this model, rationality means that consumers must always purchase goods from the neighboring consumers offering the lowest prices. As with the graphical games, there are at least two compelling lines of research to pursue in such models. The first is computational. What graph topologies permit efficient algorithms for computing price equilibria? The second is structural. What can we say about how network structure influences properties of the price equilibria, such as the amount of price variation? Here, we briefly summarize results in these two directions. On the computational side, as with the tree-Nash algorithm for computing NE in graphical games, it is possible to develop a provably correct and efficient algorithm for computing approximate price equilibria in tree graphical economies with fairly general utility functions. Like approx tree-Nash, this algorithm is a two-pass algorithm in which information regarding conditional price equilibria is exchanged between neighboring nodes, and a discrete approximation scheme is introduced. It is complementary to other recent algorithms for computing price equilibria in the classical non-graphical, fully connected setting under linearity restrictions on the utility functions discussed in detail in Chapter 5. On the structural side, it can be shown that different stochastic models of network formation can result in radically different price equilibrium properties. For example, consider the simplified setting in which the graph G is a bipartite graph between two types of parties, buyers and sellers. Buyers have an endowment of 1 unit of an abstract good called cash. but have utility only for wheat. Sellers have an endowment of 1 unit of wheat, but utility only for cash. Thus, the only source of asymmetry in the economy is the structure of G. If G is a random bipartite graph, i.e. generated via a bipartite generalization of the classical early Schrein model, then as n becomes large, there will be essentially no price variation at equilibrium, as measured, for instance, by the ratio of the highest to lowest prices for wheat over the entire graph. Thus, random graphs behave almost like the fully connected case. In contrast, if G is generated according to a stochastic process, such as preferential attachment, Barabansi and Albert, 1999, the price variation at equilibrium is unbounded, growing as a root of the economy size n.